The reigning theory is that it all began in a sudden expansion of space, the Big Bang. This was the time of the very tiny. The first microseconds set in motion the primordial era. Atoms formed within a hot soup of subatomic particles. The universe cooled as it ballooned outward, growing dim and falling into what's known as the cosmic dark ages. But gravity was always at work, particles pulling on one another. And after several 100 million years, considerable clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe planted the rich cosmic landscapes we see in our telescopes, where hundreds of billions of stars light up galaxies all across the universe. The arc of this great era of stars is defined by the life cycles of those stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is still raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity gains the edge and tips the balance. When the core of such a star crosses a critical mass threshold, it collapses in on itself. The energy released causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shockwaves can cause nearby clouds of dust and gas to collapse and catch fire to form a generation of smaller stars like our Sun. But when Sun-like stars go, their end will be more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. As their cores get heavier and heavier, over billions of years' time, fierce winds will begin to push on their outer layers, causing them to blossom out in spectacular displays. That's just what happened about 12,000 years ago to the star that's become the famed Helix Nebula. Today, we see the dying star's outer layers form a vast glowing ring. On the inside of the ring, spokes of more dense gas are being exposed by its winds. The star itself is now a dim, cooling remnant called the white dwarf. It's the size of the Earth, but about 3 million times more dense. This is likely what's in store for our Sun. A civilization distant in time may scan the Sun for planets, but they won't see Earth. Our home planet's end will have begun long before that, as rising solar luminosity gradually blasts away its atmosphere, rendering it uninhabitable. Surface water will disappear, evaporated by all that heat and stripped off by solar winds. Finally, as the Sun blows off its outer layers, they will envelop the Earth. Friction with those gases will cause this once blue world to gradually spiral through, melting into its mother Sun. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars. The stars will burn themselves out on a wide variety of timescales, depending mostly on how large they are. They'll leave remnants that grow slowly cooler. As a result, galaxies like ours will grow dimmer over time, unless they get seriously stirred up. That's what's going to happen to our galaxy. At just about the time our Sun begins setting its sights on swallowing Earth, any remaining inhabitants here will see the stars of the Andromeda galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart, or at least severely jumble each other up. If it's a direct hit, all the stars in both galaxies will gradually join together in a gigantic gigantic galactic puffball known as an elliptical galaxy. All this turbulence of the merger could stimulate a wave of new stars being born, reinvigorating this new, larger galaxy. Dust-ups like this, where galactic neighbors come together, will be common as the epoch of stars grows toward its later stages. But a wholesale thinning out of the universe is inevitable on a grand scale.